Hi, my name is Guillaume Pirot. I am Research Fellow at the Center for Exploration Targeting at the University of Western Australia. This is joint work with Mark Lindsay and Mark Jessell. Our work is motivated by uncertainty quantification and characterization of subsurface geology. In a geological exploration framework, in the early stage, we rely on surface observations and on integration of additional drill hole data. One question that arises: where is the optimal location of the next drill hole, such that we can reduce geological uncertainty as much as possible? Here, we propose to look at two strategies to explore this, and here is the following framework and the different assumptions that we make. If we have no data, uncertainty is huge. Then we can initialize geological knowledge by, because we are in a synthetic case, extracting data from existing database, such as contact, orientations, formation thickness, and associated uncertainty. We do that using the map2loop Python library. Once we have initialized geological knowledge, then we can generate an ensemble of geological stochastic realization. And basically, this is performed by data and algorithmic perturbation. To have more details about that, I refer you to my presentation in session Next Generation 3D Geological Modeling. Once we have a first ensemble of stochastic geological realizations, then we can compute different indicators about uncertainty, about geological misfit, and that can help us to identify where we should drill next. I will present you two strategies to see how we can achieve that. And once we know the location of the next drill hole, then we drill and we can add this data to our geological knowledge, and we can continue the loop until geological uncertainty is stabilized, or until it is small enough, or until we have used all our resources. I will use a synthetic case to show the strategies, and it is inspired by a Precambrian basin setting. The reference model is generated using these geological surface observations. Here you see the basal contacts. We also have some surface observations. There are a few faults here, there, this location here, and also one geological intrusion here. To initialize our algorithm, I consider the following initial geological knowledge. I assume that we have no surface observation in the northern part of the model, that we are not aware of the intrusion, and that we only have knowledge about three faults, one here, that one, and this one. To generate the geological models, we use a 3D geomodeler. So the first step, once we are here, is to generate a first ensemble of geological realizations using data and algorithmic perturbations. Once we have this, the first strategy to identify where is the optimal location for the next drill hole. The first strategy is to combine the volume of influence of your drill hole design with the concept of value of information. This concept of value of information is not new. It has been used in hydrogeology, for instance, with Wagner et al., in climate modeling by Beck and Teisberg, or in neuroscience, for instance, with Lawrence et al. The main idea is that geological uncertainty is an information and it has a lot of value. If we assume that where you have the highest geological uncertainty, if you drill at this location, optimally, you will then get data that has the most value in terms of information, because you will be able to reduce geological uncertainty as much as possible. So how do we define geological uncertainty? Here we use entropy as a measure of uncertainty. So from a set of 11 geological realizations, we can compute an entropy volume. So at each pixels, a high value of entropy in red here indicates that there is potentially a lot of variety in terms of lithologies for these specific locations between the different realizations of your ensemble. If you look at a blue pixel, the level of entropy is low, and so is the geological uncertainty. And basically, by combining this information of uncertainty and the drill hole geometry, here we assume a vertical drill hole design, so we can just compute the cumulative sum over the z-axis and apply a smoothing average to have an idea of the influence of your well, how much you will stabilize information around the location where you drill. Then, by doing that, we obtain an uncertainty map where high values in red indicates where you should drill. The second strategy assumes that we know an objective functions that indicate us at its lowest values where is the optimal drill hole location. The exploration of such functions cannot be done by exhaustive search. It would involve drilling everywhere, and it's not reasonable. We could try some local optimization technique like gradient search, but then there is a risk of being trapped in local minima. And this is why we use a global optimizer based on machine learning. Basically, it assumes that the objective function can be estimated with a Gaussian process, and iteratively, it reassesses the function over the domain to indicate the next drilling location. For more details regarding this technique, I refer you to this publication. We have tried these two approaches on 50 iterations. So let's have a look at how entropy, so the geological uncertainty, and geological misfit evolve as a function of iterations for these two strategies. For the strategy based on the value of information, we can see a clear reduction of entropy as well as a reduction of the variability of entropy. For the misfit, geological misfit seems stable through the iterations, but the variability of the misfit is reduced. So it's quite good. This first strategy is working well. For the Bayesian global optimizations, it's a bit another story. There is some decrease in the entropy, but it is not very significant. And as well in terms of variability of the entropy, but it is quite small. And hard to see if it's a statistical effect or if it's a real trend. And we can say the same thing for the misfit evolution. There is still a lot of work to do, in particular to understand why it does not work that well for Bayesian global optimization approach. One reason is because there is some difficulty to integrate data conditioning in the geological modeling engines, and maybe because of my bad coding abilities. So I'll have more look into that. Another thing that can be done to continue in that direction is to test different uncertainty and misfit indicators. At least we should do that because the first strategy seems to be working. And then we could start developing more realistic drill hole designs, also go towards a mixed approach, trying to combine and reduce both geological misfit and geological uncertainty. And then, of course, we can integrate other sources of information like geophysics and look at their relative or absolute costs. And of course, this will be sometime merging with the work of Mark Lindsay on data collection and value of information framework. You can have a look at his talk in the session Advancing Technologies in Mineral Exploration. With this, I would like to thank our partners and sponsors, and thank you for watching this video.